Okay, good morning, everyone, and thank you for joining us. I'm Becca. Excuse me. I'm Becca from the Media Relations Office here at AGU. The press conference that will be kicking off our day is entitled Rising Heat and Changing Climate, coming to us from AGU and the University of Washington. We will begin with each of the panelists giving brief presentations describing their work, and then we'll open it up to questions from reporters in the audience. We will end on the hour or when there are no more questions, whichever comes first. On-site reporters will be able to meet with on-site panelists in the quiet room in room R05 next to the press room on the second floor after the press conference is over. Reporters, because this is a Zoom webinar, you won't be able to turn on your video or microphone. So if you would like to ask a question, please type your full name and affiliation into the chat, please type your full name and affiliation into the Q&A box, not the chat. And we will request that you unmute yourself and then invite you to ask your question live. Alternatively, if you would prefer to just ask your question through text, you can type your name and affiliation as well as your complete question into the Q&A box, and Liza, my colleague, will pose it to the panelists on your behalf. And we'll respond to the questions in the order that they come up in the Q&A box. You can write in your question at any time, but we won't ask it to the panelists until the Q&A session has begun and the panelists are finished presenting. And reporters, please do note, please do check that your Zoom name is accurate so that we can easily find you in the participant list and ask that you unmute yourself. Slides and additional materials from this press conference will be posted to the Press Information Exchange on AGU Connect, and we'll drop a link to that in the chat. This press conference is being recorded and the recording will be posted to AGU's YouTube channel, and we'll link to that in the Press Information Exchange as well. Please bear with us should any technical issues arise. If Zoom webinar goes down for some reason, we will switch to holding this press conference through a teleconference line. And if that does happen, we will immediately send out an email to panelists and attendees with instructions for accessing that teleconference line. Otherwise, if you experience any technical issues during this press conference, please email news@agu.org and we can get you set up. And with that, I'll now turn it over to today's panelists.
Hey, good morning. Nick Bond. I'm a research scientist at the University of Washington, the College of the Environment, and the climatologist for the state of Washington. Next slide. It got hot in the Pacific Northwest, but you know that. Here, just to illustrate how hot, I'm showing time series of the temperatures in Seattle at top and Portland below. The blue lines show the range of the minimum maximum temperatures each day from the start of June till near the end of August. Those red and blue traces at top and bottom of each show the maximum temperatures for that day of the year. And so highlighted is the event, the worst part of the event west of the Cascades, where we reached 108-degree temperatures in Seattle and 116 degrees Fahrenheit in Portland, both very comfortably records. Also note how warm the minimum temperatures were during that heat wave, and the range of maximum to minimum temperatures is that kind of brown band in the middle. And so it only got down to, in the 70s those nights, and that has important health implications. All right, next slide. This event was actually well forecast, and what I've reproduced here verbatim is a zone forecast from the Seattle National Weather Service Forecast Office showing they had a heat warning out on Thursday. The very hottest day was the following Monday. They had a excessive heat watch earlier than this, but in particular for that Monday, the hottest day, they were predicting record temperatures well ahead of time. So we did have a few days lead time. Of course, we'd like more, and it's beyond our capabilities to get, forecasts a month ahead of time or so, but there were some forecasts. Okay, next slide. Just to set the stage here, It was real. We had a severe drought in the Pacific Northwest also. What this map shows is the percentile of precipitation for the months of April through June relative to normal, kind of preceding our heat wave. And where there's the red color, it was the driest ever in a record going back over 100 years for those 3 months, where it's the kind of tannish colors there. It was in the bottom 10%. So a very dry landscape. Next slide. That's just confirmed by the soil moisture. Everywhere it's brown here. It's in the lowest 2% in terms of how much moisture there was in the soil. And that has an important implication, as you can see in the next slide, in terms of the energy from the sun then goes into heating the ground rather than evaporating water from the ground, or because the vegetation is drought stressed, from transpiring water from the vegetation. And so the drought conditions both promote a heat wave. The heat wave worsens the drought, and it can just kind of ratchet itself up together. And there's a lot of recent work on that connection between drought and heat wave, some of it in Europe, getting to be some more here in the US also. Next slide. There were some tragedies involved, and I expect you're aware of this, but a tremendous toll, human toll there. Depending how you count, whether it's excess deaths for that time of year, or whether you count by where, my understanding, excessive heat is put as the primary cause of death. Either way, you get numbers close to 1,000 folks in the Pacific Northwest that lost their lives during this heat wave. And so again, just a tremendous toll. The very lowest bullet point there, the number of heat-related emergency department visits was amazingly high compared to this time of year, something like 70 times as high. Next slide. And I think this will do it for me, is that, climate change is the elephant in the room here, right? And in particular, we're seeing in the Pacific Northwest, elsewhere also, is a real systematic rise in minimum temperatures in the summertime. And these are really important. And as you can see that, as my very first slide, the minimum temperatures during the height of the heat wave were record setting also. And this is something that we're just going to have to deal with more and more. So I appreciate your attention, and I think I'm going to be handing it over to Dr. Ebi. So thank you.
Thank you, Dr. Bond. That was an excellent introduction. I really appreciate your remarks. I'm Kristie Ebi. I'm a professor in the Center for Health and the Global Environment at the University of Washington. Next slide, please. A few days after this event, or the day after this event ended, we moved into July. And if you're not aware, July was the Earth's hottest month ever on record. You can see some of the temperatures around the world, and you can see that the land surface temperature over the Northern Hemisphere was about 2.8 degrees Fahrenheit above average. So truly a remarkable month. This heat dome did not contribute to that, but it is important to know the heat dome is in the context of a particularly hot summer worldwide. Next slide, please. It's well understood how our bodies react to higher temperatures. Our cells and our organs operate within a pretty narrow range. Our body has developed a range of mechanisms to help protect our organs when our internal heat starts to rise. We're all familiar, of course, with sweating to try and cool you down. And when sweating and other factors, moving to a place that's cooler, like sitting under a tree, having access to mechanical cooling, when those are insufficient, then our core body temperature starts to rise. That affects our internal organs, our heart, our kidneys, our lungs. When you look at the excess deaths after a heat wave, about 50% of all of those deaths are due to cardiovascular disease. So lots of strain on the body. Because it's possible to intervene on these, we can say that people are suffering and dying unnecessarily, that these deaths are preventable. And we look at these deaths, but there's also other issues we need to look at, occupational health and productivity, for example. There was an impact on agricultural workers in the state of Washington. It was the height of our cherry season. So there was a big impact on the workers there as well. And we know that climate change is increasing heat-related morbidity and mortality without urgent investments in research and in risk management. Next slide, please. The Lancet Countdown is an annual effort to track 44 indicators around how climate change is affecting our health. The most recent version of the Lancet Countdown was just published a month or so ago. This shows how vulnerable to heat has been rising worldwide since 1990. Countries around the world are categorized into the Human Development Index. This takes into account not just GDP, but also education of the population and life expectancy. And you can see across the various categories of the Human Development Index a real increase in vulnerability. Next slide, please. And that is paired with increasing exposure of vulnerable populations to heat waves. This shows you on the left-hand side, adults over the age of 65, on the right-hand side, children less than 1 year of age. And you can see the numbers, that the exposure of adults over the age of 65 since about 1986 to 2005 increased by 626 million person years of exposure. That was for children. For adults over the age of 65, it's 3.1 billion more person days of exposure. So significant increase in vulnerability, significant increase in exposure. Next slide, please. A recent analysis did a formal detection and attribution study looking at what proportion of heat-related deaths worldwide, well, it's based on 40-some countries, are due to climate change. And the overall conclusion was about 37% of all heat-related deaths are due to climate change. In the Pacific Northwest, because of a detection and attribution study here, that concluded that the event was virtually impossible without climate change. The proportion, of course, is much higher, that most of those deaths during that heat wave would be attributable to climate change. Next slide, please. Working Group 1 from the Intergovernmental Panel on Climate Change had the report published this summer. I'm sure you're all aware of that. And you can see the increase from 1850 to 1900, sort of pre-industrial, but not really pre-industrial, through to various warming levels. Of course, we've already warmed more than 1 degree C globally. And you can see on the right for the 50-year events that we're already seeing 1 and 50-year events almost 5 times more often than during pre-industrial temperatures. The event that occurred in the Pacific Northwest was much rarer than a 1 and 50-year event. And then you can see the projections out at 1.5, 2, and 4 degrees C of an incredible increase in these 1 and 50-year events as we move into a much warmer future. Next slide, please. And there's lots we can do about this. Most heat-related deaths are preventable. These are some options for how to help protect people, both at the individual level on the left and a variety of strategies on the right for buildings, our urban strategies to ensure that we adjust our infrastructure to a much warmer future, and we make sure that people are aware of the kinds of actions that we can take. As Nick noted, we did not have a heat wave early warning system that would provide that kind of warning here in the Pacific Northwest. I'm sure that by the next heat wave, we will have something in place to help protect our population. Next slide, please. And with that, I'm handing off to Ashok. The floor is yours.
Yeah, thank you, Kristie. So I'm Ashok Mishra. I'm an associate professor at Clemson University. So I'm going to talk about increasing risk of extreme events under climate change. Next slide, please. So just to give an overview that we are seeing there's an increase in the temperature historically. And as we move forward under different emission scenario, we can see there is a gradual increase in the temperature. And in addition to that, there is also increase in the population projections for different scenarios. So when there is increase in the temperature and increase in the population, so the impact of temperature likely to have more on the population. And also due to the increase in the temperature, there are different types of extreme events. One is heat stress, that's a single extreme events, or there can be a compound extreme events, which is a combination of drought and heat wave occurring simultaneously. And also this can result in the water scarcity. So when there is an increase in the temperature, increase in the population, so the impact of heat stress likely to be 2 to 3-fold that I'm going to discuss in my future slide. And the heat stress has got significant impact. My previous panelists, they have extensively discussed on this. In addition to the heat stress, the drought is also substantially impacting the socio-economic sectors, multiple sectors, with an annual loss of $9 billion per year. So the question is, how these heat-related extreme events likely to change in the future, in the space, as well as in the time, and which are the critical hotspot or the critical regions that likely to witness more extreme events. Next slide, please. So just to start with the spatio-temporal variation of heat stress, if you look at the left-hand side figure, between 1980 to 2020, there is a gradual increase in the heat stress, and using a threshold of 40.6 degree, we can see that as we move forward, there is the heat stress likely to keep increasing in the future. And if we compare the two lines, for the extreme events like heat stress severity RCP 8.5 and temperature RCP 8.5, we can see that the heat stress is increasing faster compared to the temperature, because the heat stress is a combination of both temperature as well as relative humidity. When you look at the spatial pattern, we can clearly see at the present time the southeast, then the southwest, then Pacific Northwest. So these are some of the regions that we are already seeing the heat stress. And as we move forward, we can see the severity is gradually spreading over larger areas. And if we move to the further far future period, we can clearly see the heat stress is dominating southeast, Pacific Northwest, southwest, and its impact likely to be higher in the future. Next slide, please. Now, we formulated a metric to quantify the impact of the heat stress. So what we did is we considered 3 variables. One is the high-end heat severity. That means we look at the extreme heat severity that is calculated based on the 40 years of return period. And we also look at the heat acclimatization, which is very important for the human body. The reason is if there's a gradual change in the heat stress, then our body can able to adjust that. But if there is a high fluctuation, let's say today it's 95, tomorrow is 105. So in that range, high fluctuation that will impact more to the human health. In addition to that, we also included the population exposure. As I mentioned, as for the future, there will be change in the population distribution. So considering these 3 variables, we formulated a metric to quantify the potential impact of heat stress. And just to give an example, the heat acclimation, if you see the right-hand side figures, the one under 1D heat stress, you can see the northeast region, typically the heat acclimatization was less, but as we move forward in the northeast, we can see there's a gradual increase in the heat acclimatization. So that means this may impact the heat stress will have more impact in these regions. Next slide, please. So we quantify the potential impact of summer heat stress. First, we look at the population effect, simply based on the population. That is the right-hand side, the column, the plot. So here we can see there are few regions we see the impact is more. But when we look at the climate change impact, we can see distinctly the northeast, as I mentioned, the heat acclimatization is increasing in these regions. And some of the regions in the Pacific Northwest and Southwest. But when we combine the climate change and population effect, we can see there's a higher impact, which is the first column under total effect, you can see. So a lot of areas, they're going to witness the impact more than threefold, what we are seeing now. So specifically in the Northeast, Pacific Northwest, Southwest. So these are the regions where we see there will be high impact of combined influence of climate change and population effect. Next slide, please. Then I'll discuss about the compound events. In the case of compound events, we are going to see two events simultaneously. In this case, one example is drought and heat wave. You can see in this picture that the rectangular lines that has been drawn, you can see those are the time frame where we see that drought is occurring. On top of that, heat wave is occurring. So individually, the drought has significant impact. It can reduce the water storage, reduce the hydropower, energy production. And during the time of heat wave, we need more energy. So that means the impact will amplify more and more in the future. So this is this picture is from the study area, the latitude and longitude provided below. So next slide, please. So the top right plot figure, you can see that the temperature anomaly, so beyond 2000, year 2000, we can see there's a gradual increase in the temperature. Those are plotted with the red bars, and the blue bars represents on the negative side. So what we are observing is beyond 2000, since the temperature is on the positive side, so how does it impact the compound, drought, and heat wave at a global scale? So we calculated the frequency, the compound, drought, and heat wave frequency. So what we are noticing is we are going to see one to three more events per year in the future. I mean, sorry, in the last 2 decades, we have seen 1 to 3 more events compared to previous 2 decades. Similarly, the duration of compound, drought, and heat wave events, the duration likely to increase by 2 to 10 days per year. So in this case, if you look at the spatial maps, USA, we can clearly see these are the regions that is likely to see more compound events in the future. So next slide, please. So to conclude, the potential impact of short to medium duration, like 1 to 7 day heat stress events, likely to increase more than threefold across densely populated regions of the US, example, Northeast, Southeast, Atlantic coast, Midwest, by late this century. The contribution from climate change alone is likely to double the impact of compared to the human population on the coastal Pacific Northwest, Central California, and Great Lake regions. And due to the regional amplification of increasing the temperature, we're likely to see more compound droughts and heat wave events. So with that, I'll stop here. Thank you.
Hi, my name is Cassandra and I'm a researcher at Washington State University. So as we've seen from the previous talks, heat waves have been increasing in frequency, they've been getting hotter and they've been getting larger. But what's not well understood currently is how compound heat events, and Ashok touched on this briefly, but here I'll be explaining 2 different types of compound heat events. The first is simultaneously occurring large heat waves in the Northern Hemisphere, and the second is combined heat and humidity extremes. And these results are from 2 of my recently published papers shown on the screen here. So we know heat waves can have quite dire consequences, but when 2 or more heat waves occur at the same time, the impacts can be even greater. So for example, if we have 2 or more crop regions affected by heat-related crop losses at the same time, this can lead to issues with food security or rises in food prices. The figure on the bottom of the slide here shows the 29th of June 2021, where we had 5 heat waves occurring in the Northern Hemisphere, as shown by the red patches on this plot. And so this was one day during the Pacific Northwest heat wave in North America. Next slide, please. This figure here shows the change in the number of days with simultaneously occurring large heat waves in the Northern Hemisphere mid to high latitudes. And we refer to these as concurrent heat wave days. So we saw in the 1980s, we had 20 days per year with 20 concurrent heat wave days per year. Whereas by the 2010s, we were seeing an average of 143 concurrent heat wave days per year. So this means that almost every day from May through September had 2 or more heat waves occurring in the Northern Hemisphere. Not shown here, but we also found that heat waves, these concurrent heat waves were getting larger and they were getting hotter. Next slide, please. So as well as how the number of concurrent heat waves changed, we wanted to know why they were changing. While we found that the majority of the change was due to global warming, we also examined the amount of change due to changing atmospheric circulation patterns. And we found there was a small influence in changing circulation patterns. So these 2 figures here show geopotential height patterns, but if you're not familiar with that term, just think of it as being very similar to a high pressure chart, a pressure chart where red shows high pressure or high geopotential height and blue shows low pressure or low geopotential height. And so we found in our study that these 2 circulation patterns were increasing in frequency and were driving a small portion of the increase in current heat wave days. And this was associated with increases in heat waves over Eastern North America, Europe, China, and some Arctic regions. In our second study, we looked at we compared trends in the number of days with dry heat extremes and the number of days with humid heat extremes. So dry heat is measured just using a normal thermometer, and it's the temperature we're used to hearing every day. But humid heat requires both high dry temperatures and high humidity. High humid heat can pose additional risk because at a certain point when the humidity is too high and the temperature is too high, it gets to the point where the human body can no longer cool itself by sweating and heat illness can become a real risk. So this figure shows on the red, in the red line, this shows the increase in the number of people exposed to dry heat extremes per year. So we can see there's quite a strong increase in the number of people exposed. Then we can see in the blue line, there's an even stronger increase in the number of people exposed to humid heat extremes. Next slide, please. This plot here shows the increase or the change in the frequency of humid heat days around the world, where red shows an increase in frequency and blue shows a decrease. In the 3 boxes I've highlighted here, we see 3 regions where we've got some of the strongest increases in the number of humid heat days occurring. So this is occurring over Northern South America, parts of coastal Africa, and South and Southeast Asia. Next, please. This next figure shows the magnitude of the extreme humid heat events. So because we've defined an extreme event based on the local climatology, we have hotter heat extremes in the tropics than we do have in the Arctic. And looking at these 3 boxes again, these are the 3 regions I highlighted on the previous slide where frequencies are increasing the strongest. This shows that in these regions, we've also got some really high humid heat extremes, with the red colours indicating what is typically considered to be a dangerously hot temperature. So we found that where we're getting the largest increases in frequency of these events, these are also where a lot of these regions, these events are dangerously hot. So yeah, we know that these events can be quite detrimental to human populations as well as animal populations, but some communities are more vulnerable than others. So this includes elderly and children. It also includes people without access to air conditioning or people who've lost access to air conditioning due to another event or power outage. And it's also really important to consider for outdoor workers. So for seasonal farm workers in particular, it matters when the event occurs. So if it occurs during the planting or the harvesting season, the impacts can be worse. and we wanted to look into this a bit more. So I'll now pass it over to Conor, who's leading the research on this topic.
Hey, good morning, everyone. I'm really excited to have a chance to talk with you all today. My name is Conor Diaz. I'm an undergraduate researcher at Columbia University, and I've been working with Dr. Rogers and some other great folks across Columbia, Syracuse, and Washington State, looking at some uniquely human impacts of rising humid heat across the globe. So many impacts to the food system are formulated in terms of crops themselves, like impacts to the yield of a crop or disease spreading across plants. But here we look at the human dimension of the crop workers out in the fields. So what we've sought to characterize here are the risks across the world of working in dangerous heat, trying to take into account variability in the timing of agricultural activity, across the world. Next slide. So one of our main findings is that the amount of cropland that's exposed to dangerous heat and dangerous working conditions has increased over time. We see positive trends across crops with notable spikes during strong El Nino years. In the figure shown here, most notably, we can see the blue X line on top showing rice cropland exposure roughly doubling from 1979 to 2019. And in 2019, the world saw about 5.9 million square kilometers of rice cropland exposed to more than 2 weeks of dangerously hot and humid heat in what we call the agricultural labor season, which we define as both the planting and the harvest season for a given crop. Next slide. Overall, we found that the risks to crop workers vary across crops and seasons. However, consistently indicated regions include South and Southeast Asia, the Amazon in South America, and also Western Africa. Shown here is data from 2016, a strong El Nino year, with the dark red regions indicating more than 2 weeks of dangerously hot and humid heat, landing when crop workers were either planting or harvesting rice in this case. Next slide. So what's new about the work that we've done here? There does exist a growing body of research on agricultural workers in the context of climate change, but so far it's focused on public health data, stuff like mortality and injury data concurrent to heat events. It might look at economic impacts or taking qualitative surveys of crop workers in the field, or otherwise looking at regional model projections of climate data. So far, there doesn't exist research that takes into account the differences in the timing of agricultural activity across the world. Different crops in different regions are planted and harvested at different times. Lastly, there's yet to be made a global analysis characterizing the heat risk to agricultural workers from these extreme events. Next slide. So how did we go about doing all of this research? So what we did, we combined a number of data sets to basically locate these dangerously hot days within local planting and harvest seasons for a set of 25 crops. We took global crop calendars, data on the real harvested area of crops, climatological data from 1979 to 2019. This is a historical study. And we used a threshold in wet bulb temperature to count these days. We use wet bulb temperature as a proxy for human heat stress. A lot of the panelists so far have mentioned how we think about heat stress and the human health impacts of dry bulb temperature, the regular heat that we feel outside, and also the compounding effect of humidity, reducing our ability to lose heat from sweat. So we put this at roughly 27 degrees Celsius wet bulb, which is about 80 degrees Fahrenheit. And we counted the number of days in each of these regions, each of these seasons that were exceeding that threshold. Next slide. So with all that being said, let me leave you with some implications of this work. So most importantly, we found that agricultural workers are facing increased risk from extremely hot and humid weather. We have roughly a doubling of the number of exceedances of our threshold over land over the study period. This is important information because adaptation strategies really need actionable climatological information that takes into account heat stress experienced in seasons that are specific to the management of certain crops. Global food systems could be strained. Namely, workers in Asia are facing some of the fastest increases in the number of these dangerously hot days that land when they're working. Ultimately, moving forward, global agricultural practices will really need to change with a changing climate, not only because there are risks to the crops themselves, but also risks to the workers who are vulnerable in this warming climate. Thank you all so much.
All right, big thank you to our panelists, and we're going to go to the question and answer part of our session. Reporters, a reminder, if you would like to ask a question, please put your name and your affiliation into the Q&A box, and we will invite you to open your mic in the order of the questions are received, or if you prefer, you can type your question there, and I will read it out to the panel for you. Our first question is going to be from Seth Bornstein with the Associated Press. Seth, go ahead when you're ready.
Thank you. In terms of looking at this, let's look at adaptation issues on this. Have you, when you look at places like Chicago from the 1995 heat wave, Philadelphia from their heat wave, second and tertiary heat waves, even though they're higher in terms of temperature and humidity, seem to have less of an effect because of methods put in to lessen it. In general, what are the lessons learned from those places, and can they be put in to a place like the Pacific Northwest, where heat waves generally are so infrequent that it may not pay off? Can you discuss the implications of, sort of learning from other northern cities for the Pacific Northwest?
I'm happy to start, if that's all right.
That's great.
Thanks, Seth. It's a great question. We've learned from earlier heat waves, as I said before, that almost all deaths in a heat wave are preventable. And we know that heat wave early warning systems and heat action plans work. There's been heat waves, for example, in Scandinavia in recent years. There was one in Sweden that was associated with 700 excess deaths. Same time, there was heat waves in Finland and Estonia. Setting up a heat action plan, which includes a heat wave early warning system, is not expensive and it's not difficult. The key elements are having somebody with convening power where you can bring together all of the relevant groups. So not just health and meteorology, but you want to make sure who looks after the elderly care facilities, who reaches out to the red line districts, who interfaces with emergency management services. In our area, who is going to be reaching out to the agricultural workers, to the farmers, to ensure that they have the information that they need. And it involves basically coordination. Many of the systems have 2 meetings a year, one at the end of a summer season, what did we learn? And one at the beginning of the next year, where you get all the partners together and say, right, we're heading into the summer season. Make sure that everybody's coordinated, that you've got the correct cell phone, that people haven't changed jobs, they don't have a new cell phone number, and talk through the actions you're going to take. And that can make a really significant difference. There was a webinar not long ago talking about the heat dome from the perspective of emergency management departments around the region. And it was really remarkable hearing their stories of what happened. They didn't have specific ways to cool down people. People were coming in extremely hot. And one of the emergency departments put people into body bags and put ice into the body bags to help cool them down. One of the emergency departments was taking a call every 9 minutes of somebody in trouble with the heat. There's lots we can do in advance. So we can't stop the heat wave, but we can stop the suffering. We can stop these unnecessary deaths that occur.
Well, look, if I could just follow up on that in terms of, in other places, we have air conditioning. I mean, and in, even cooling centers for people who don't have air conditioning, and that sounds like there wasn't any. And that, I mean, is there talk of creating cooling centers, increasing air conditioning? And then, of course, when you increase air conditioning, it comes at a cost of carbon dioxide emissions. I mean, air conditioning often warms the world. Can you address that? I mean, sort of the whole issue of air conditioning and cooling centers there.
Cooling centers are critical. They were set up kind of at the last minute here in Seattle. They were also set up in Portland. Portland ran into a challenge because there was an implicit assumption that people could take their metro system, the tram system, to the cooling centers, but it got so hot they couldn't run them. So you do have to work with all the partners of how hot does it get before we turn off the tram system. So yes, they were set up. Yes, they made a difference. We don't have estimates yet of how much, but those things can be set up. You need to set them up again in advance. People have to know where they are. You have to think through, you've got an older adult, someone who's got chronic medical conditions. Are you expecting them to walk to the bus, to wait for a bus to take it to the cooling center during the heat of the day? So working all of that out in advance. In terms of the air conditioning, there's been some pretty interesting work from a group of physiologists at the University of Sydney, led by Ollie J, looking at where you really need to have air conditioning and where you can use some of those other measures that I showed on my last slide of having people sit in front of a fan and put water on your skin so that the water evaporates and cool you off. And in the Pacific Northwest, we can get by without having air conditioning. As you noted, we don't have heat waves very often. Nick noted that as well. So there's a whole range of options that are available, and making sure that you've got those planned, people know how to use them, that they're ready to deploy them when we do have a heat wave, means that we don't have to air condition everything. And in the long run, it's going to be better for us physiologically to start adapting to higher temperatures, because temperatures are only going to continue to get higher. You happy, Seth?
Yes, thank you.
Maybe our other panelists like to chime in on that question. Sorry, I accidentally muted myself. We're going to go to Selvaraj Samarlingam with a question for Cassandra Rogers. Extreme humid heat could extreme humid heat represent the more hurricane activities? Is there any forecast or prediction on that?
Yeah, great question. I haven't looked into hurricanes myself, but I know there's a really clear example of how hurricanes can influence these types of events. So Hurricane Ida, which actually occurred here in New Orleans, there's evidence that there were more deaths associated with the heat wave that followed that event than from the actual hurricane itself. And as Kristie mentioned, these are largely preventable deaths from extreme heat. And so what happened is, in a lot of cases, power went out, lots of people lost power, which meant even if they had a house that should be really comfortable, has really good air conditioning, that was just completely lost. And so these houses got stiflingly hot. The heat lasted, I think it was 4 days. And that's where people had a lot of issue with extreme heat. So yeah, as Kristie mentioned, things like cooling centres where people can go to get relief from heat are really important. But yeah, other than that, I'm not any more familiar with projecting how hurricanes.
If I could just add to that a little bit, tropical cyclones are part of the climate system, and they effectively transport heat and moisture from lower latitudes to the middle latitudes. And so they can, exacerbate, hot temperatures and high humidities in that way. And Cassandra makes a great point, though. What we've seen, especially if your power is knocked out and suddenly you have this really hot, humid air mass, then that just makes it that much worse. So.
Next question is from Sarah Kaplan at the Washington Post. Go ahead when you're ready, Sarah.
Hi, thank you guys. I'm curious about, so this heat wave in the Pacific Northwest, the rapid attribution study that was done found, not long afterward, that it was virtually impossible without the effects of climate change. And I'm wondering, can you talk a little bit about like what, does this represent kind of a new era where it's not only that like we're experiencing heat that's made worse by climate change, but things that were not possible in a world unaltered by people are now, like there's something sort of fundamentally different about the heat that we're experiencing now. And also the heat, what does that mean for the future in terms of the types of heat waves that people and communities need to be preparing for?
I'm happy to start on that. I was involved in that study, and it was a significant scientific effort to do that. It's not a simple task to do those kinds of rapid detection and attribution studies. There was a very strong collaboration of authors, and I want to specifically acknowledge that one of the key authors was Jan van Oldenburg, who sadly died a few weeks after that study. The study was done through the World Weather Attribution Collaboration. That is an unfunded activity. And certainly one of the lessons learned was how powerful that was, that having that done more or less in real time was incredibly important for decision makers to see that, yes, climate change really did influence that event. It was almost impossible to estimate a return period for that because it was so rare. I earlier mentioned some heat waves a year or two ago in Scandinavia. The estimate for the heat wave in Sweden is it was a 1 in 3 million year event, which I personally find very hard to wrap my head around. And we know from all the work of the Intergovernmental Panel on Climate Change and all the climatologists that contribute to it, that heat waves are increasing in frequency, intensity, and duration. And we are seeing these very extreme extremes. There's also a heat wave that was determined that could not have occurred without climate change in Japan. So yes, we are seeing these very extreme extremes. And the Working Group 2 report said we should just plan for those. We're going to see more of these going into the future, that we're putting more energy into the climate system. And one of the ways it's coming out is through these very extreme events. Did that answer your question, Sarah?
Yeah, I mean, I guess so. Like the record in Portland, for example, broke previous records by like something like 9 degrees Fahrenheit. So is that should we all be ready for like, if to experience temperatures that like are basically unthinkable or that we once thought were unthinkable? Like, should every city be prepared for heat waves that are potentially 9 degrees or more than their previous records? Like,
I would say that not one size fits all, and it kind of depends there. And so, sorry, I can't give you a more specific answer, but one thing that is from the study that Dr. Ibai mentioned is showing in just a couple of decades, the kind of heat waves that we're seeing now that are so extreme that'd be, 1 in 1,000 year event or something, are supposed to be happening now, about once every 10 years. And so the frequency is in general apt to go up, but again, it's going to be kind of site specific. And yeah, so I'm personally reluctant to give a kind of hard and fast number there for, the world as a whole.
And I would add to that, every place does need some kind of heat wave early warning system. You need to have those discussions of what are you going to do if that happens. I read this week, and I apologize, I don't remember where, somewhere in the Arctic had a temperature over the summer of 100 degrees Fahrenheit. And if you're not prepared, what happened in the Pacific Northwest is just classic of what happens in a region that's not prepared. Of the scrambling to open up cooling centers, the scrambling to try and get information out, even though there was forecast it was going to be really hot. Over 1,000 excess deaths. These people would not have died without this heat wave. And so having those discussions, having the planning, it's not hard. It's just thinking about what are you going to do if something like this, which is unthinkable, does happen. And another example is in 2003 was a massive heat wave across most of Europe. There was over 70,000 excess deaths. What many people don't know is the following year, there was a very, very high heat wave in the Netherlands. And there was over 1,200 excess deaths. They didn't have a heat wave early warning system because they thought they were too far north and that they wouldn't have that kind of a heat wave. So yes, we don't know what's going to happen. Seattle may go for years without another extreme heat wave. But we don't want people to die. We don't want agricultural workers to suffer when they happen. So that preparedness is important for everywhere because we don't know what the future is going to bring with our climate.
Can I just add something there? So it's a good question, like, should we prepare for these events that are like 9 degrees above what we've experienced in the past? But when preparing for extreme heat, we don't necessarily need to know by how much we're going to break that record. Even if it's a non-record breaking heat wave, it can still have really bad consequences. And a lot of the steps we need to take are going to be very similar regardless of how extreme the extreme is. So things like making sure there's cooling centres, making sure people can get there, anticipating power outages, having a heat alert system, as mentioned earlier, all these things are going to be crucial for average heat waves as well as for the off the charts heat waves.
Our next question is from Catherine Cornai, a freelancer. It's for Conor. Of the 25 crops you studied, are most of them also affected negatively by heat and humidity? In other words, are we dealing with both a human issue and an agricultural issue, or mainly a human issue?
Yeah, thanks, Catherine, for the question. So I'm not an expert on impacts to the crops themselves. It's it would be hard to say for humid heat specifically. We looked at a variety of crops. You have stuff like rice that's grown in paddies, and then you have stuff like maize that's just grown in fields across the world. So it's difficult to say, to look at the impacts of humid heat. Crops are negatively impacted certainly by dry heat extremes. But what I can say is, we do have a variety of crops that were exposed across the study, from stuff like soybeans, rice, maize, sorghum, potatoes. But that's the most I can say about the crops themselves versus the exposure to the workers in the fields.
I'll add quickly to that following that 2003 heat wave, there are multiple studies about the big impact on crops and the reduction in productivity from the very high temperatures. But you're right, you need an agronomist who can weigh in on that.
Yeah, and certainly in this heat wave in the Pacific Northwest led to some real large agricultural losses. Potatoes, wine many of us enjoy wine. It needs cool temperatures at night to have the proper sugars. And there's some evidence that in some of the most prime wine growing parts of the world, that the temperatures are getting to the point that it won't be as great for the wine. So, talk about it hitting close to home, right? So, but just again, in the Pacific Northwest, potatoes, wheat, apple, and berries, they all suffered in this past heat wave.
And Nick, do you want to mention the mussels and clams?
Well, yeah, there was, this got some attention right at the time. There was a tremendous die-off of invertebrates in the tidal zone there, and particularly mussels in the waters of British Columbia that happened to be the low tide when there were the hottest temperatures, and they basically cooked in place. And just a tremendous toll. We're not sure how long it'll take for them to bounce back, but there were massive die-offs, and my understanding is the beaches didn't smell so great there for a while.
Next question is from freelancer Liz Payton. Is there a probability distribution of risk associated with elevation, the way there is one associated with latitude? Are higher elevation communities insulated in any way?
If I may jump in, I'm not familiar with this research myself, but one of my co-authors has been looking into humid heat at high elevations, which he gave a talk earlier this week. So research is being done on humid heat at high elevations. And I'm happy to look into that some more if you want to email the question.
Do we have any further questions from members of the press in our audience? All right, we're just at the top of the hour, so I'm going to close this question and answer session and turn it over to Becca for final comments.
Thanks, Liza, and thank you.
There is a question still in the Q&A from Mamatha.
Martha is not a member of the press.
Apologies.
So I would just like to thank our panelists for their time this morning and for sharing their research, and for all the reporters who asked their questions and attended this press event. I would just like to note that our next press conference is on intensifying storms and climate change, and that will begin at 11 a.m. Central Time. And just in case you have muted all of your notifications from AGU Connect, there was a breaking announcement that Secretary of the Interior Deb Haaland will be giving a virtual keynote speech at 11:20 a.m. Central. Glad that they overlap, but that's okay. Thank you again for your time.
Thanks, everyone.